Hello and welcome to the Cyber1 YouTube channel. My name is Fred and this video is part 4 of the Walking Robots series, The Power of Movement. This video we will look at the power needed to rotate the various joints at the rates we need. Let's get started. When it comes to movement, there is some effort or work that is involved. The faster you want something to move, the more work that is needed. The SI system, the unit of work is the joule. 1 joule represents the work done by a force of 1 Newton moving 1 meter in its own direction. U equals F multiplied by D. W is the work done by the force F newtons which moves a distance of d meters. W is clearly in Newton meters, from which we see the Newton meter is the same as a joule. Rotary systems like our robot joints, it is more convenient to work in terms of torque and angular distance, rather than force and linear distance. These are closely as we can see by considering what happens when a tangential force is applied at a radius r, from the center of rotation. The torque is simply given by torque equals force multiplied by the radius. Suppose the arm turns through an angle of theta radians, so that the circumferential distance traveled by the force is radius multiplied by theta. The work done by the force is then given by work equals force multiplied by radians multiplied by theta equals torque multiplied by theta. Note that whereas in a linear system work is force times distance, in rotary terms, work is torque times angle. The units for torque are Newton meters, and the angle is measured in radians, which is dimensionless, so the units of work done are Newton meters, or joules, as expected. Find the power, or the rate of work. We divide the work done by the time taken. A linear system, assuming that the velocity remains constant, power is given by power equals work divided by time equals force multiplied by distance divided by time equals force multiplied by v. The lowercase v is the linear velocity and lowercase t is the time required to travel that distance. The angular equivalent of this is given by power equals work divided by time equals torque multiplied by theta divided by time equals torque multiplied by w. Where lowercase w is the constant angular velocity, in radians per second. Just a reminder, there are 2 pi equals 360 degrees. Okay, now we got that bit out of the way. Let's look at how much power each of our joints is going to use. The toe joint. From previous videos, we know the max static torque will be 4.8 Newton meters. The rate of rotation needed will be at least 225 degrees per second. Using the formula power equals torque multiplied by angular velocity. We will first need to convert the degrees per second to angular velocity, which is in radians per second, which we can do by multiplying the degrees per second with 2 pi divided by 360. Pi divided by 360 multiplied by 4.8 Newton meter multiplied by 225 degrees per second equals 18.850 watts. We look at the higher rate of rotation where the toe was pitching. Down at 681.8 degrees per second we get pi divided by 360 multiplied by 4.8 Newton meters multiplied by 681.8 degrees per second equals 57.118 watts. The ankle X joint. For the ankle X joint, the max static torque is 11.4 Newton meters. The rate of rotation required is 42 degrees per second. Pi divided by 360 degrees multiplied by 11.4 Newton meters multiplied by 42 degrees per second equals 8.357 watts. Had thought this one would need more power, as it has to hold the weight of the body, but then the foot is not that long. The ankle Y joint. For the ankle Y joint, the max static torque is 4.92 Newton meters. The rate of rotation required is 600 degrees per second. Pi divided by 360 multiplied by 4.92 Newton meters multiplied by 600 degrees per second equals 51.522 watts. The ankle C joint. While we have an idea of the rate of rotation from Ray's video, 75 degrees per second, we don't know what the torque will be, which makes this impossible to calculate. We'll have to come back to this when we can calculate the dynamic torque on this joint. The knee joint. This joint has the greatest rate of rotation and torque combination of all the joints. For the knee joint, the max static torque is 27 Newton meters. The rate of rotation required is 299 degrees per second. Pi divided by 360 multiplied by 27 Newton meters multiplied by 299 degrees per second equals 140.900 watts. This motor will have the greatest load on it. As a result, it will need a more powerful motor than the rest of the joints. The hip X joint. For the hip X joint, the max static torque is 27 Newton meters. The rate of rotation required is 54 degrees per second. Pi divided by 360 multiplied by 27 Newton meters multiplied by 54 degrees per second equals 25.447 watts. The hip Y joint. For the hip Y joint, the max static torque is 6.3 Newton meters. The rate of rotation required is 20 degrees per second. Pi divided by 360 multiplied by 6.3 Newton meters multiplied by 20 degrees per second equals 2.199 watts. The hip C joint. While we have an idea of the rate of rotation, we don't know what the torque will be, which makes this impossible to calculate. Should be noted that these calculations are for the required power to move the joint and do not make any allowances for the losses as a result of power conversion from electrical to mechanical motion, or for the losses associated with friction within the joints. We will cover losses in power conversion from electrical to mechanical motion in more detail when we look at how electric motors work in another video. If you like this video, then please click on the like button. You may even want to subscribe and click on the notification bell to be notified when more videos like this one are released. If you have any questions, then please leave a comment below. Ray does try to answer them all. All of this costs you no money and helps us to create more content like this video for you. If you would like to help the channel out further, then please consider becoming a Patreon supporter. There is a link in the description. We look forward to seeing you in the next video.